All right, class, looks like we're live. Welcome to this first day of virtual learning. So we're going to be talking about the central limit theorem today. So this is actually 6.4. So I'm going to write that out here. This is lesson 6.4. We're still in chapter 6. This is going to be the last section in chapter 6, but chapter 6 is all about the normal distribution. We talked about, we did a lab on how to determine normality. We did a lesson on determining normality using those various techniques. But now we're going to talk about a special theorem called the central limit theorem. So we're going to use this to solve problems involving sample means for large samples. All right, so that's our lesson for today. So let's go ahead and introduce the central limit theorem. So just like in the labs that we did, which involved dice, those were discrete distributions, right? That because those were discrete variables because you roll a die and you get a number from 1 through 6. So let's say we have an example discrete distribution. Discrete means whole numbers, right? So in this case, this is our discrete distribution given. It's not like a die experiment because there's no 2 there, and we know in a die there's an actual 2 there, right? On dice. So let's just pretend that this is another experiment. Now, so what happens is the central limit theorem holds with continuous and discrete. Remember, continuous is when you don't have to lift your pen to draw the curve, right? So you can have decimals in between. Discrete is whole numbers. So look what happens when we take this discrete distribution and let's just say that these represent cards. And the cards are labeled 1, 3, 4, 5, and 6. All right, there is no 2 because there's no 2 there. All right, and then we're gonna take 4 cards from our deck. From this deck, and we take the 4 cards. The first 2 cards are 1, right? And then the last 2 cards are 3 and 5. Okay, so that's my first sample. So we took our sample. Then we go ahead and do another trial, another sample. We put the cards back, and then we shuffle them, and then we take another sample. So I'll take a 1, let's say I took a 4, a 5, and then a 5 for my next set of 4 cards. And I repeat this a few times until I get 5 trials, okay? A total of 5 samples, right? We call those samples. And what we do is for each sample of 4 cards, 4 numbers, we are going to average those samples together, okay? So for each sample of 4 cards, I'm going to average those values. So I'm going to take my first sample here, I'm going to average those. So I'm going to add those up together and then divide by 4. All right, so we're going to do that on the calculator real quick. So this is 1 plus 1 plus 3 plus 5. And then we're going to divide that by 4. So if you do that, you get 2.5. Okay, and that represents our sample mean. Remember, x bar stands for the sample mean, the mean of our sample here. And then we're going to continue doing the averages for the other samples of 4 cards that we have. All right, the next sample is 3.75, the next sample mean. The next sample mean is 3.25. Another one, another 3.25. And then the last one is 2.75. Okay, so we got our 5 sample means. Now what we're going to do is we're going to take those sample means and we're going to plot them on a chart. We're going to do a dot plot for this. Okay, so I already got it ready. We got our number line with our numbers here. And I'm going to go ahead and stack dots for each number. So for 2.5, I got 1 dot there. 3.75, I got another dot there. 3.25, a dot here, another 3.25, so I'm going to stack that, and then 2.75 here. So very interesting. We have a look. If you look at the original discrete distribution, it is definitely not a normal distribution. But if you were to do the averages of the samples that you take, and you plot those averages, then the averages will form a normal distribution. So if you look at this, this kind of looks like a bell curve. And if you do this for multiple samples, you're gonna find that you're gonna get a normal distribution, which is a very interesting finding. So the original distribution doesn't have to be normal for the average distribution to be normal. Okay, so if we So this is basically the central limit theorem. So as the sample size grows larger, so as the sample size becomes larger, the frequency distribution of the sample means will become normally distributed, which is what we were seeing firsthand. So when we took the averages and we plotted those averages, those sample means, that became a normal distribution, even though the original distribution wasn't normal. Okay, so now for this, so this is for n equals 4. This is what we were doing earlier, right, with the 4 cards. Now, if we do this multiple times and take multiple samples, like I said, you're going to get a dot plot that resembles this. This is just a bunch of different dots, right? And the average of that will be, the average of the original distribution, which we said for us, was around 3.25. But if you, and notice that it forms the bell curve, right? If you increase it to n equals 20, right, the sample size is increasing, then that means that it'll become more normally distributed, right? So it's becoming more normally distributed than when it was n equals 4. And the mean is still going to be the same, right? The mean is still going to be the same value in the middle, right? That's going to be the same, but the standard deviation is going to be different, right? So notice that this normal distribution is skinnier, right? And this is broader. This is wider. And then the other one's skinnier. So if you continuously do more trials or increase the sample size, then the normal distribution will become more normal, but it'll be skinnier. It'll have a skinnier shape, which means the spread is smaller. The standard deviation will be smaller. Okay, and that is essentially the central limit theorem, guys. So again, the original distribution doesn't have to be normal, but when you go ahead and take samples, right, and you average those samples and you graph them, the greater the sample size that you do, if you do 4 cards versus 20 cards, right, versus 30 cards, the more, when you do those averages and you plot them, it will become more normally distributed and skinnier. Okay, so that is the central limit theorem. So we're going to talk about that in terms of, the formulas and stuff. Okay, so as the sample size increases, the shape of the sample means, that's x bar, sample means, will approach a normal distribution. The distribution will have a mean of mu and a standard deviation of sigma over square root of n. So it won't have a standard deviation of sigma like it was normally. It will be sigma divided by the square root of n. So that's the different part there. Okay, so the mean of the sample means, what we do, there's a symbol for that, for the mean of the sample means. That's mu x bar. Okay, so that's the mean of the sample means. All right, the population mean is going to be mu. All right, so the mean of the sample means is the same as the original population mean. So if I took the averages of my x bars, right, of my cards or whatever, and I average those out, then I'll get the same original mean. Now, the standard deviation of the sample means, it's just simple for that. That's the standard deviation of the sample means. So sigma x bar, standard deviation of sample means. And that's going to equal the original standard deviation, but divided by the square root of n, okay? So what that's saying is that the original distribution will have a standard deviation of sigma, but the distribution of the x bars will have a standard deviation of sigma divided by square root of n. Okay, and that's represented over here. So the original distribution, let's just say that the original distribution was normal. Again, this original distribution does not have to be normal. Like with our die example, it wasn't a normal distribution. And it wasn't even continuous, it was discrete. But let's just say that if this is the original distribution is my x. If I take that and I convert it over to x bars, and I plot those x bars, then that will give me another normal distribution, but skinnier. Why is it skinnier? Because of this denominator. This denominator makes it smaller, makes the curve skinnier. Remember, a bigger denominator means a smaller fraction, and a smaller fraction means a skinnier curve. All right, so that's the central limit theorem. So how do we find the z-score for the X bar distribution, right? We call that X bar distribution the sampling distribution of means, by the way. That's a very important key term. So that is the sampling distribution of sample means. So when I say that, I'm really just saying the skinny version of the original bell curve that plots X bar as opposed to X. Okay, so how do we find the z-score for this sampling distribution? Well, remember that the original z-score had x, mu, and sigma. Well, this is also going to have that. So it's going to be x minus mu. So this is going to be the mu of the x bar distribution, though, okay? And then divided by sigma for the x bar distribution. So it's very similar. However, remember that the mu x bar is equal to mu, right? We said that according to the essential limit theorem, this is equal to mu, but that the sigma x bar, this is called the standard error of the mean. So we will shorten that for SE for standard error. That's going to be the standard deviation divided by square root of n. Okay, so I'll give you the new formula. So the new formula is z equals x minus mu divided by sigma over square root of n. So this is the formula that we'll be using. So as previously shown, as the sample size becomes larger, the distribution becomes skinnier and it becomes more normal. Okay, so it becomes normal but skinnier. All right. So that is our formula that we're going to be using for the central limit theorem. So let's use the central limit theorem to find the following probabilities. So we have a study that shows that children under the age of 10 watch an average of 25 hours of television a week. Assume that the variable is normally distributed. So we have an average here. So that's our average. So we'll call that mu, right? So that's 25 hours. Now it says the standard deviation is 3 hours. So that's 3 there. If 20 children under the age of 10 are randomly selected, so that's 20 children, that's my sample size. Find the probability that the mean of the number of hours will be greater than 26.3. So this is saying that the mean is greater than 26.3. So this would be x bar right here. So x bar is, oh yeah, I forgot to say that this is x bar. I apologize for that. So change that to x bar, not x bar. I apologize for that. So just make that correction there. So x bar is 26.3. And then we'll have to find out what the sigma over square root of n is. So that's going to be 3 over square root of 20. So we'll go ahead and find that because we need that for the formula. All right, so I'm going to go ahead and calculate that. 3 divided by square root of 20. So we get 0.67. All right, so we got all the information. We extracted all the information. Now, what's the difference between this and a normal z problem? A normal problem that we did in 6.2. The difference is that they're asking you to find the probability that the mean is greater than. So when they ask that keyword there, this is the keyword that you want to look for. When they said for the probability that the mean is going to be greater or less than or between, then they're talking about a central limit theorem problem. If they're asking for find the probability that the number of hours will be greater, not the mean, just the number of hours, then we're talking about a regular z problem. We don't have to do central limit theorem. Okay, so this is the sampling distribution of the sample means. Notice that I drew this curve skinny, right? This is a skinny normal distribution, as opposed to the broader one, the regular one. Okay, and this is because we're graphing x bar. If we were graphing x, it would just be the wider one. All right, so we got our skinny normal distribution. The middle of that is going to be the average, right, which we said was 25. However, we're not going to go by our standard deviation here. We're not going to go by sigma. We're going to go by sigma divided by square root of n. So we're going to be using this number right here to go by that, okay? So that means we're going to be doing 25.67. And then we're going to go ahead and add another 0.67 there. And this will be 26.34. And then the last one is 27.01. And then we're going to subtract to get, subtract 0.67 to get the other numbers. and we get 22.99. Okay, so those are my new numbers. Again, we're not going by sigma, we're going by sigma divided by square root of n because we're using the central limit theorem here. So now they're asking for the mean number of hours they watch television is greater than 26.3. So that means we're talking about around here. So this is my x bar is 26.3, and we want it to be greater than. Greater than means shade to the right. So I'm going to go ahead and shade to the right, right there. Okay. So now we got our sampling distribution sample, means we drew our diagram. Now let's calculate the z-score. So to calculate the z-score, remember, you got to use the x bar minus mu divided by sigma over square root of n formula. My x bar is 26.3, right? That's what they're asking for. All right, sorry about that. It was a little glitch there. So we're back online. We should be back online. Okay, so we're going to go ahead and plug in x bar, 26.3 minus the mu is 25 divided by sigma is sigma divided by square root of n was 0.67. So we're going to go ahead and get that value. This is a 0.67. Apologize for the handwriting there. All right, we get 1.94. So that's going to be my z-score. All right, so then once we get that z-score, remember greater than means to the right of z, and to the right of z means we need to do 1 minus. So we got to do 1 minus the z value, right, or the probability. So we're going to do 1 minus the probability that z is less than 1.94. So we're going to look at 1.94 on the z chart, remember the normal distribution chart, and then we'll do 1 minus that. Okay, so we're going to do 1 minus that value. Okay, so we're going to go ahead and look up the value. So we're going to I'm going to reference the Z chart here. So let's go ahead and pull that chart. Let's see here. So referencing the Z chart, and you can look up the Z chart on the class materials folder, or you can just look it up on any website. You know, most websites have these tables. So we're going to look up for 1.94, and that's going to be right there. So it looks like it's going to be 0.9738. Okay, so we got to do 1 minus that. And we got 0.0262. And that's going to be my probability of getting a sample mean greater than 26.3. All right, so let's go ahead and do another problem real quick. We're just going to do one more problem. So we're going to use the central limit theorem to find the following probabilities. So the average length of a time a computer is used is 96 months with a standard deviation of 16 months. If a random sample of 36 computers are selected, find the probability that the mean of the computer age is between 90 and 100 months. So it says probability that the mean, so that means x bar, so that means that the mean age, so this should be x bar 1 and x bar 2. So x bar 1 is 90, x bar 2 is 100. Okay, and it says the random sample of 36 computers, so that's my n. So I need that. It says the average length of time a computer is used is 96 months. So that's my mu. All right, and then the standard deviation is 16, so we'll put that there. So now we're going to go ahead and calculate sigma divided by square root of n. Square root of 36 is just going to be 6, so I got to do 16 divided by 6 basically. And I get 2.7. I'll just round it to 2.7. Okay, so now we're going to draw our skinny bell curve. In the middle, we have our mu, which is 96. Again, we're not going to go by our sigma here. We're not going to go by 16. We're going to go by 2.7 because we're using the central limit theorem. Okay, so we're graphing x bar here. So we have, let's see here. So we're going to add 2.7 to this, and that's going to be 98.7. Add another 2.7, that's going to be 101.4. another 2.7, 100 and 103 point, okay, it should be bigger than that. It should be 104.1. Now we're going to go ahead and take away 2.7, so I'll just do that real quick. We get 93.3, 90.6, and 87.9. Just to save us a little bit of time there. So now we're interested in the probability that the mean is between 90 and 100. So we're going to go ahead and 90 is around here. So that's my x bar 1 is 90. And 100 months is around there. So x bar 2 is 100. And we're going to shade in between those. All right. So we're going to go ahead and shade in between those. All right, so that's our curve and that's our distribution. Okay, so it looks like we're getting a lot of hiccups from the system. So let's continue. Let's finish up this example, and this will be it for the video. So now we got the curve. We drew it. We shaded. So now we need to calculate two z-scores. So we're going to call it z1 and z2. So again, we're going to be doing 90 minus mu divided by sigma divided by square root of n, and we already did that earlier. That was the 2.7 number. So we got 2.7. Calculate that, and then z2 we got 100 minus 96 over sigma over square root of n, which we did that earlier. So let's get those two numbers. The first one is negative 2.22. The last one is 1.48. So we got our two z-scores. So now what we need to do is we need to look up both z-scores and then subtract the areas for both z-scores. Remember, if you have two z-scores, you got to locate them on the table and then subtract them. Remember, the bigger minus smaller. So we're going to do the probability that z is less than 1.48. That's the bigger z-score, minus the probability that z is less than negative 2.22. So we're going to look up both those and get our answers. So let's look at 1.48 on the chart. So 1.48, this is the 8 part, and 1.48 is 0.9306. 0.9306. And then we got our negative 2.22 that we got to look up. So we got to go to the negative side. All right, negative 2.22 is 0.0132. All right, we're going to go ahead and subtract those and get our final answer. We get 0.9174. So the probability that we get a computer age, that we get a mean computer age between those two is 0.9174. All right, so that is the central limit theorem. It's very similar to what we did before, but you just got to remember that sigma over square root of n. There's a few little differences here and there. But that's it for the lesson, guys. I hope you took a few things from this, and I'll see you in the next one.